Good morning, good afternoon, and good evening. I'm Tom Concolino, and I'm here with our presenter, Akhilesh Tripathi. Thank you all for attending Rigaku's webinar, and this is the second session of our Practical XRD with Confidence series. And today we're focusing on quantitative XRD. Now, please note that if you missed any of our previous webinars, you can review them on the Rigaku website. Now, this is going to be an interactive session, and we'll be taking your questions live during the webcast and answering them during the session, so please don't wait until the end to ask. Please submit those questions via the Q&A button at the bottom of your screen. Now, I won't be monitoring the raised hand function, and I'll be using the chat section to post related links. We will try to answer as many questions as we can during the webinar, and we'll respond to any unanswered questions after the session is complete. If, for whatever reason, you have difficulty viewing the webinar live, please note that it is being recorded and you'll be able to view that recording beginning tomorrow. And with that said, I'll turn it over to Akhilesh.
Thank you, Tom, for the kind introduction. Excuse me. Again, good morning, good afternoon, and good evening to everyone joining us from around the world. Welcome to episode 2 of our XRD webinar series. It's a pleasure to have quite a few participants today. In this session, I'll be discussing quantitative XRD, its principle, methods, and practical applications. Again, thank you all for taking time to join us, and I hope you find today's webinar informative and valuable. So, in the past webinar series, we have covered the basics of XRD. So what I have planned today is I'll cover the recap of XRD basics. I'll talk about common XRD quantitative techniques, choosing the right method, what suits you, common mistakes, and some case study. So let's begin with XRD basics. So recap of XRD basics. So essentially, whichever XRD instrument you use, you have an X-ray source and a detector, like is shown here in this cartoon. You'll bring your powder sample, and in some cases, bulk samples. And then 3 situations arise out of the diffraction. Situation 1, you will get a crystalline powder diffraction, such as the one shown here. You may also get, if your material is amorphous, an amorphous hump, usually called hump, around 22 degrees, such as the one shown here. Or you can get a mix of crystalline plus amorphous, sometimes also known as a mesophase, which is an intermediate state between crystalline and amorphous form, exhibiting properties of both. It has some degree of molecular order, but not a long-range order. And it retains the fluidity like an amorphous material. I also want to mention today that our x-axis usually in the cases scattering angle 2 theta or d spacing, and our y-axis is scattering intensity, usually raw counts or counts per second. So we begin this by considering the fundamental information that can be obtained from a standard X-ray diffraction pattern measured on a diffractometer, such as the one shown here. So if you look at this, there are 2 parts here. The navy blue sharp peaks are the crystalline component, and the light blue hump is an amorphous. If you take the integrated peak ratio of the 2, you can get the percent crystallinity of this material. If you take the width of the peak, popularly known as full width at half maximum, you get information about crystallite size and strain. Peak positions are very indicative of lattice parameter, and the pattern as a whole gives you information of phase identification and something what we will learn today, quantitative analysis. Let's move to the next slide, the phase identification. As you saw in the previous webinar, we discussed at length, my colleague, Ekaterina, that phase identification is almost like fingerprints. So you have a phase A, for example, some material, let's say this is quartz and this is, let's say, cristobalite, 2 different phases. You can have a mixture of several phases as if there's a mixture of fingerprints, and you would normally use a database to identify each fingerprint, i.e. each phase, what it belongs to. So you have reached to this point. You have identified phase, like let's say, what are the most common quantitative XRD technique at this point? Tom, I understand there's a polling question at this point.
We do. So I've just launched it. And since this is a webinar on quantitative analysis, the question is actually starts right off with that. So if you do quantitative analysis, what method do you currently use? So we have semi-quantitative analysis, which is the RIR. We have whole powder pattern fitting Rietveld, calibration curve, amorphous phases, other, and I don't. So we've got a lot of answers coming in, and Akhilesh, they're going right up your alley here. We have a lot of Rietveld users. So we'll let this go for another 30 seconds or so, and then we'll end the poll, and I'll share the results with everybody.
Yeah, I see.
Make sure they all have time to answer.
Mm-hmm.
Let's see. Okay, looks like it has slowed down. So let me end the poll, and I'll share those results for everyone to see. So yeah, so 50% of our viewers here already do Rietveld analysis and perhaps some direct derivation, and then actually 1/3 of them don't do any. So this is actually a great subset of the diffraction users we normally see. So I will stop sharing, and you can go ahead and continue on, Akhilesh.
Excellent, Tom. That's a very good thing. We have we are dedicating a significant portion of this talk to the Rietveld and DD also. So that's good to know these results. So before you get a very good quantitative result, I believe you should have a very good sample prepared. It is very relative to that. So there are many errors you could create in a good quantitative study if your samples are not well prepared. So let me point out some of the best ways to prepare samples so that eventually you get a very good quantitative result. The surface of the sample must be exactly level with the edge of the holder. We'll show you this with the picture so that it's clear what's the idea here. The depression in the sample holder or the well of the sample holder should be completely filled unless you're using a low background holder. What I mean by low background holder here, like some of us have this flush zero background holder, also known as zero background holder. And usually we employ it when we have very small amount of sample or in certain clay preparations. Those one you can have a micro layer of sample on top of them. The particle size should be 10 to 40 micron. We know that if the particle size are larger, it doesn't represent a random sample and could have preferred orientation. In the same coin, if it is below a certain size, you could have errors due to the peak broadening, which we will also cover, known as microstrain or strain broadening. So 635 mesh in another unit. The sample should be firmly packed because it gives rise to a dense sample and will give rise to a better diffraction pattern. Footprint of the X-ray. This is something we should also take care as long as the beam is not spilling out of the sample, because once a beam is spilling out of the sample, scattering from the holder or the surrounding may increase. Air scatter can also contribute. It could also give rise to higher background noise and poor signal to noise ratio. Weak peaks may disappear. So as much as we can try, we should in order to keep the constant volume condition, we should keep the footprint of the X-ray constant on the sample. Homogeneously mixed sample, but that's a big yes, because if your sample is not homogeneously mixed, it doesn't represent a true sample for a quant work in order to quantify each one of the phases. Preferred orientation. I will dwell on this topic more because it's a very important point. There are methods to prepare less preferentially oriented sample, and later on, with the help of the software, you can also reduce preferred orientation. So those things needed to be taken care of before we get into a good quantitative work. Sample preparation. As we mentioned, that sample preparation is very necessary part of getting a good quantitative result. So let's quickly see how to prepare a good sample. So pour the sample on an indented section of the holder, whichever holder you're using. It's valid on all of them, like the one shown here. Spread and pack the sample evenly. So you are spreading the sample onto this holder in these two pictures. And then third step, you move to make sure the sample is right up to the brim of the sample holder. In this 2D picture, I hope you can make it out. The sample is not under or overfill. This is very essential for getting a good peak position in order to identify all your phases, which eventually will be utilized for the quant work. Clean the sample holder surface. This is a good practice to follow, just to keep your diffractometer clean and not to take any sample which is dropping from the sample holder. So in order to kind of emphasize how good it is or how important it is to prepare a good sample, this is a picture that shows when the sample is well prepared, as shown in this one, smooth and well packed surface. You get sharp peaks and matches well with those purple lines from the database. But when the sample is just on the sample holder without being prepared well, it can give rise to shadow errors, displacement error, and a number of others. Not only the peaks are not sharp for the same sample as in the previous picture, but also the purple lines from the database are displaced. So such could be the consequences of not preparing a sample very well. So now we have the essential ingredient. We learned in the previous one how to find your phases. We learned quickly how to prepare a good sample. So we are ready for a comprehensive review of the quantitative XRD methods. So there are three main semi-quantitative methods, RIR. Semi-quant, when people use the word semi-quant, what do we mean by that? It means estimating the approximate amount of the phase in a sample, but not with full quantitative accuracy, i.e., you could have an error of 1 to 3% easily. And later on, we will discuss that in light of seeing some results. So RIR stands for relative intensity ratio, and it's our first method called semi-quantitative methods. The next one is whole powder pattern fitting, WPPF, and one of them is Rietveld, the main one, and direct derivative DD analysis, which we will also cover. The Rietveld refinement is generally considered quantitative XRD method, not semi-quant. Once we take care of a number of things, and that's what we are going to focus today. However, people sometimes use the term semi-quant for Rietveld too, and it's not wrong. There are situations when Rietveld itself becomes semi-quant. Everyone may understand that sometimes we have poor counting statistics, strong preferred orientations that we cannot take care of, inaccurate crystal structures, poor fitting, if you can't do a good fitting, incorrect peak shape modeling, limited 2 theta range, bad sample preparation. Those can actually make a Rietveld also a semi-quant. So we have to keep that in mind, and that's what we are focusing on, how to get the best results out of Rietveld and DD analysis. And the next one is quantification with calibration curve. We have heard about this a lot, and I'll cover this about the 3 different calibration curve methods that are available. At times, I also hear a lot from our customers, they want to do quantification of amorphous phases. So we will look into that aspect too today. Examples of special quantitative applications. You can develop a part of the software to do specialized quantitative applications, such as one known as respirable silica. You might have heard this trick, or dust analysis. There is a dedicated, usually a software routine to do that. What we do in this is calculate the crystalline silica in a workplace air or chrysolite asbestos in bulk sample, just to ensure that the air quality is to an intended level and not below it. There is a method called retained austenite too, which is to know the amount of alpha iron and gamma iron in a steel. A nice balance of the two produces a steel of our choice. I will not be covering these 2 dedicated quantitative approaches in today's talk, but I just wanted to make sure that there are dedicated software you are aware of to do quantitative work. Next, when do we want to use the 3 methods that I just mentioned? RIR, relative intensity ratio method, Rietveld, the quantitative method by modeling, and the calibration curve. So in this session, we will cover these in detail, RIR, Rietveld, and calibration, with a focus on when to use each. I will revisit this slide afterwards to compare these methods and talk about these points that I have written, like pros and cons, benefits and limitation of each one of them, to establish a clear guidelines of their selection in your quantitative work. So let's begin with the first one, RIR method. So why RIR? Because the sample has, when you take an entry to match with your phases from the database, it has a RIR number. Next time you will notice. So the RIR means the sample highest for your sample in the XRD, the highest peak has been compared with alpha AL2O3 or purandum. So it then generates an RIR number, i.e., the ratio of your highest peak to corundum. So when you are using RIR method, like shown in this picture, for example, there are two phases in this material, anatase and rutile. The highest peak of anatase is 101, TiO2 101, and rutile is 110 TiO2. So the software will select them, or you can choose to select these. And now, as we know, these two peaks have an RIR, these phases. So essentially, using the scale factor, because they have the common denominator, just by using a single peak of each, we can tell the percentage of the two material, i.e., the quantitative numbers as shown. So quantitative values are calculated using RIR number from the database from the integrated intensity of the highest peak. Now, what are the controls one has when one uses RIR? Usually the software itself selects the highest peak of each of the phases present, like in this case, anatase and rutile. But you have a choice. If this peak has an overlap with other peaks, you could choose the next highest peak, and so on and so forth. But that's pretty much all the controls you have. The method itself is relatively simple because you're choosing. I just want to share one story with this method so that it kind of gets you in the idea. Several years ago, maybe I'm talking about 15 years ago, when I visited a lab, in those days, people used to print XRD pattern on chart paper. And I have met this person who would, with this technique that were used in those days, you will cut the highest peak of each of the phases with the scissors and put them in a fine microbalance. So if this gives you some sort of an idea, that's how this technique originated. But these days, modern computers can, of course, find the integrated intensity of the peaks by just measuring the peaks. And you are using a relative intensity ratio with alpha alumina. But that's kind of the origin of this method, which I have seen myself visiting long time back at us. So next is calibration curve method. As shown here in three pictures, there are three different methods: external standard, internal standard, and standard addition or spiking methods. So in external standard method, you compare your unknown sample to a series of sample whose composition is already known. For example, you add 20, 30, 40, 80, 85% of some sample. And by seeing how strong the signal is with these reference sample compared to the reference you have, you can estimate how much phase is present in your sample. So that's external standard method. Internal standard, as like the picture depicts, you add some sort of internal standard, a known reference material directly into your sample. Then you compare the sample signal to the reference signal inside the same mixture to estimate the amount present more accurately. The last one is standard addition, also popularly known as spiking method. You add a known amount of material you are trying to measure into the sample itself. By observing how much the signal increases after each addition, you can calculate how much was originally present in the sample. So let's see, like in action, how would the graphs look like for the three methods: the external, the internal, and the standard addition method. So as I was saying, in external standard method, you have 20, 40, 60, 80%, and somewhere your sample is, let's say, around 20%. So it will fall near here in this line, and you would know the weight percent. I'll show another example of this in the next slide. In internal standard, you have an internal standard, a consistent one. Let's say a 10% reference sample is added, and you're doing pretty much same thing as external standard, but it is a little superior because any changes in the internal standard upon measuring, you can relate it to the same amount to the unknown sample you are trying to know. For example, I mentioned dust analysis or respirable silica. Respirable silica is usually sprayed on silver membrane, and silver membrane amount is fixed, let's say 10%. So if in the measurement it shows 11.2%, you know that 1.2% is the error that can happen in your sample too. So that's how an internal standard helps you to further correct your calibration curve study. Standard addition. So, for example, you have a certain species, a phase, and then you want to know how much that phase is present, but you have a pure form of that phase too. So you will add, let's say, 2, 3, 5, 10, any number of percentage of the same phase into the sample, and then extend the line towards the x-axis to know how much was originally present in the sample. I think we still need a few slides to show these. So let me show another slide for external standard. And I've shifted the percentage amount of each phase on the x-axis, the 2 theta axis, 20, 40, 60, 80. So you can relate that the integrated intensity of the peak is proportional to the amount of sample you're putting, i.e. like 80% sample has the highest peak compared to the 20% sample. The integrated intensities are proportional. And let's say you bring a test sample, which is close to 60%, as shown here in blue. And then what you will get, you will see, yes, the software says around 58.6. Now, we did put 60%, and it shows 58.6. With an ESD, estimated standard deviation of 5, which often people ask me, what does that mean? It means 58.6 plus minus 0.5. So that's the error in that number. But however, overall, there is still a 1.4% error. Now, we should understand that calibration curves are sometimes not as linear or approximately linear over a limited range. But they can become nonlinear due to microabsorption, overlapping of the peak, crystallinity differences, preferred orientation, amorphous content, and matrix effects. So these things can cause slight nonlinearity, and hence we should always expect some errors within them. What about the standard addition or spiking method? It is interesting, so I wanted to show this also with an example. This is a pharma example of two pharma medicines drugs, talbutamide form 1, the polymorph form 2, which has a peak here. You can see the polymorph 2 has a peak here. Now, if we want to know the content of this, suppose we are working to manufacture this drug, and there's the polymorph 2 appears sometimes, and we want to know how much it appears. So what you would do is you will keep adding some X percentages to it, such as 0.4% or 0.7% and 1%, and extend this line to where this intensity, integrated intensity belongs, and you would know, okay, in the original sample, we have 0.478% of form 2 present, as shown here with that extended line. So that's how you can determine, but you realize you need to have a pure form 2 to be added to this sample to get its original amount present in the sample. Okay, so with that, I shift gear to one of the most liked one in the survey, the Rietveld method, or in big picture, we call it whole powder pattern fitting method. And I will explain why we call it whole powder pattern fitting method. But the main program is Rietveld analysis. It could be present. You might have used this program in several other names, but its origin or the main formula that is used, which was Dr. Hugo M. Rietveld's thesis, was this nonlinear least square function. So we have a nonlinear least square function here, which is over whole powder pattern with a weighting scheme, where your model, the model that you will make out of your phases, you want to bring that model, which looks like your powder diffraction pattern, as close to your observed powder diffraction pattern. So this sort of equations are used a lot nowadays, but originally Dr. Hugo M. Rietveld presented in his thesis, PhD thesis, this, and in the open literature, that this sort of program will bring my pattern very close to the original pattern, and I can know everything about the pattern. So this is known in there are several versions of this software, such as GSAS in general structure analysis system, full prof suite, mod, or Ritica. These are all other programs, very detailed one, exactly on the same principle by Dr. Rietveld. So that's the idea of Rietveld analysis. And let's dig a little bit deeper into this program to understand, so that when we use this program, we could utilize all the features that are available in this program. So first, what is a Rietveld program doing? The least square refinements are carried out, as I shown you with the previous equation, until the best fit is obtained between the entire observed powder diffraction pattern and the entire calculated pattern. I have emphasized on the word entire here because the previous program, what RIR we saw, we were just considering a peak. If we didn't like that peak, we will jump to the next peak. But Dr. Rietveld said that powder diffraction pattern already has too many overlaps. You are presenting the information in two axes, this y and theta axis. So it's a two-dimension. And if you have, let's say, 7 or 8 phases, and then you may have severe overlap. So why to leave any part of powder diffraction pattern not utilized? So hence his program has become very popular because it uses every part of the pattern. And the program will generate a model or so-called calculated pattern, which will be fit on the original XRD data that you collect on any instrument. And when the fit is very good, and we will see what factors determine it is very good. Essentially, it is masking the pattern completely, which is shown here in the difference pattern, that the difference between the calculated pattern in blue, shown here in dots, and the original data, red, is very good. And hence the difference is minimized, so you get a good model fitting now. And that's the idea of Rietveld program, fitting a model to as close as possible to the XRD pattern that you collect on your instrument. Tom, we have a polling question now.
We do. But actually, we've had some good questions come in, Akila. So I wanted to get a couple of these out of the way now. So the first one here is actually, we have two of them from the same attendee, and they're actually excellent. So one is, can you use the Rietveld method with the constant area illumination, i.e., variable slits? And so, can you do those measurements, or does Rietveld allow for the refinement of those data points?
So let me get this question straight. Can Rietveld be used if you are collecting data with a variable slit mode?
That's correct.
Usually, most of the software convert the data automatically without your knowledge into a fixed slit type, because this is how the origin of these programs were in those days, when such a luxury of doing a variable slit wasn't available. So it's usually done. However, if I come back to your question, can we use it with variable? And suppose we are not converting into a fixed slit type? Yes, you can. But remember, the peak intensities are compromised at lower and higher angle when you go to fixed versus variable. So as long as you are able to take care of this, either through preferred orientation correction or some other type of correction, then you should be good. I would suggest very quickly in this, run a sample where you mix two known phases. Let's say you mix quartz with salt 50-50 and try to run and see how close you are, because you are adding 50% of both of them. So you could relate to how close is the result between the two different formats, and that will give you a lot more confidence. I always tell a beginning user to prepare a mixture by themselves and try this. Tom?
Okay. Thank you. And then the second one here is again from the same user, is when you're doing a quantification of amorphous content using internal versus external standard, how would these two compare from an error standpoint? Which one would you think would provide more accurate results, internal versus external, for the amorphous content?
Yes. Very good question. Usually we handle amorphous with an internal standard, but the caveat is that internal standard, choose one. For example, I can say zinc oxide or corundum are very two popular ones. I'm sure you're aware of those two. Inorganic sample and do not change over a period of time. Both are inorganic samples. But I have a few caveats again. Make sure their peaks are not overlapping with the phases you are thinking about too much, because that's always a case. So you have to choose your internal standard judiciously, which one is not too much overlapping. Second, the reason why internal standard is superior, because like I mentioned briefly in the earlier slide, and I actually use it sometime in the cement amorphous, I add zinc oxide to calibrate the quantitative result well, so I was saying that make sure the peaks are not overlapping. And secondly, The internal standard provides you internally the corrections. If zinc oxide, when you say 10%, if you are adding 10%, then it gives the amorphous amount a correct number because you have one component of your phase exactly known to you. The other components you are still trying to get. But fixing the one component because you're adding it in a fixed amount makes your amorphous results very good. So as long as there is not too much overlap, internal standard does better than external standard.
Okay, perfect. All right, one last question, then I will launch the poll for everybody. So you show glass holders, obviously, in your earlier slides. The question is, right, aluminum holders are just fine for this as well, right? There's no reason to have any specific type of sample holder.
It's a good question. Incidentally, just yesterday, I had a case where a customer said, I'm seeing some aluminum peaks in my aluminum sample holder. Then I asked him, what sample are you putting in here? He said, carbon. I said, carbon is a low Z material, just atomic number 6, atomic weight 12. So I advised him, you could, if you don't mind amorphous peak, you could go to glass or zero background. So as long as your materials is inorganic, mineral, clays, cements, there is no difference between the two. But if you are using organic material, which is carbon, hydrogen, nitrogen, oxygen, the game of that, or just graphite carbons, which is a low Z material, you should always be careful not to use the shallow one. There are two types, for example, from Rigaku, a 0.5 millimeter or a 2 millimeter. Use the deeper well one, so that the X-ray does not penetrate and reach the bottom.
Okay. All right. So from there, let me go ahead and launch the next poll question. And it's been on the screen here for everybody to read. So hopefully we'll get some quick answers. So if you do quantitative analysis, how many phases do you typically analyze? And it's just going on in order here. So we want to see the complexity of what our attendees observe or are working on. Wow, got a lot of answers quickly here. So
what do you think is going to win, Tom?
Boy, well, I mean, looking at the answers as they come in, it's interesting. We see a pretty wide spread, in fact. So we'll give this just a few more seconds here, since we do have a few more answers coming in. All right, we'll go ahead and end, and let me go ahead and share those results. So Akhilesh, we have a lot of users doing more than 5. That's a lot of refinement, especially since half of the group does it by refill. That's a lot of thinking. So, and so then again, 1 through 4 make up obviously the majority, but we've got a group of people here that do some pretty heavy lifting. So from there, we'll let you go ahead and continue. Thanks, Akhilesh.
Thank you, Tom. This is actually very good for me to know, because when we are going to compare the 3 methods, the people who are doing 1 or 2, or I can even say 3, can afford RIR, because the chances of overlap are minimized if you have just 2 phases in your sample. But definitely if you have 5 or over 5, I believe, and we'll see this again, retweet is a choice by far. Okay, so that's very good poll numbers for me to kind of emphasize these points later on when I'm going to compare the 3. So let's move on to the next slide. So now we are going to in the refill, people I've seen, I mean, over several 30 years of my career in this direction, I've seen refill is often underutilized, if I may use that word, which means it's a very strong program, but you may not be using all the bells and whistles or all the functions that are within these programs. And I hope I can do it justice today to make people realize the powers of this program to get the best results out of it. And I begin this with saying how to get the best rate-willed analysis done to your sample. Let's begin with having first point, good 2 theta range. I've seen sometimes people just go from 10 to 40 degree in inorganic or clay or minerals, or 10 to 50. No, it's a big no-no because low angle helps lattice parameter, higher angles improve atomic position and thermal parameters. Every data point is considered in the read world, so you should collect the data to as much as possible. Now, I'm not that pushing by saying that I'm not saying collect every data up to 140 degree in organic, but at least 5 to 100 or 5 to 90, I would say that's the minimum for me, is a good range. Now, if you have organic, because of the scattering length of carbon, hydrogen, oxygen, and nitrogen in organic tends to decay. It's because of Caglioti function towards the end. So you don't need to go above 55 or 60. You will see no peaks after 55 or 60 if you have organic or pharma sample. But for inorganic or clay or mineralogy, there's definitely a 5 to 100 is a very good range. Well-grounded powder, we have emphasized, but we can emphasize on this again, 10 to 30 micrometer. The line broadening effect will be visible with smaller particles and larger crystallites is never representing a random sample. It's full of preferred orientation and which will affect our quantitative analysis. Point number 3, it is essential that data be collected appropriately. What do we mean by that? So usually, if you will see, there should be a 5-step across the top of each peak, which we say as FWHM, the full width at half maximum, the thing that I showed in the second slide, should be divided by 5 or 7. So a lot of people sometimes I've seen use 0.001 as a step size. No need to go that small. You will create kinks in the database, but no need to go big step sizes such as 0.06, like 5 to 90, 0.06 step size at a speed of 5. 0.06 may be too large a step size. So usually the good step size turnaround for good intensity sharp crystal material 0.01 or 0.02, which most of us put it, but without realizing the reason for that, it creates 5 good points and creates a good peak shape, which is essential to our quant. The next 2 points, I have been very blunt here, writing that do not try to smoothen the diffraction data. This is a big no-no. Because what happens in Rietveld refinement, the way the data is interpreted is XRD data are assumed to follow Poisson statistics, which is random counting noise from photon event. The refinement algorithm uses this noise level to give proper weights to each data point. So remember that weighting scheme we wrote, and I'll show it again in the equation, what calculates. So when you smoothen your data, you artificially reduce noise. You change the true uncertainty each point. You destroy the correct weighting scheme. So it's good for a post representation to smoothen your data, but do not try that. Similarly, please do not remove background. Background contains real information and should be usually modeled. We have modeling function for both the peak profile and background, so we don't need to smoothen or remove them. And again, removing a background can not only remove some weak peaks and alter the phase fraction, but can also create negative intensities. So we don't want to use it. So that's about how to collect a good data and what not to do in Rietveld refinement. The next point is, what does Rietveld refinement need from you? Phase identification. That's something you are doing and putting, and then the program begins. And it's best if you have crystal structure information. And we will emphasize why crystal structure information in next few slides. But I also want to mention one thing that I promised. Remember, it was written WPPF, whole powder pattern fitting. What if there are certain materials for which crystal structure have not been found? Some of you, if you work in minerals, know that smectites such as montmorillonite do not have a crystal structure yet known to human beings because it's a disordered structure. It's hard to get the molecules at a place. It's constantly moving. So when you somehow cannot, for a certain phase, out of let's say 6 phases you have, you mentioned you are using 8 phases. You have a montmorillonite phase, for example. Now, montmorillonite doesn't have a crystal structure. Then the refinement automatically shifts for that phase to a Pauli or labile refinement, which is refining individual peak intensities while fitting the full powder pattern using structure. So for those, we are not using structure. That's why we said whole powder pattern fitting. We still fit the whole powder pattern, but one of the phases is fitting just as profile fitting using the integrated intensities of the peak. So these 2 professors, gentlemen, scientists, Pauli and labile, developed this, and it automatically comes into play in most of the Rietveld programs that you use. With that, let's move into why so much emphasis on crystal structure and diffraction data. So I want to mention things one by one so that you can focus, like, for example, position XRD feature, what it represents and what it is controlled by. such as the position of the peak. When you see a diffraction pattern, you see the peaks at different positions. They come and you see width of the peak and you see intensity of the peak. So the position of the peak are very indicative of the crystal structure. They come from crystal system, space group, lattice parameters. So when you choose a phase with those, you are generating positions of the peak. Your width of the peak is coming from microstructure, crystallite size, lattice strain, defects that are in your phase. Intensity comes from atomic arrangement directly, atomic position, occupancy, composition, thermal vibration. Those are contributing to the intensity of your powder diffraction pattern, the intensity of the peaks in the powder diffraction pattern. So I promise just one more slide on this point about intensity relation with the crystal structure. So this is internally in the program, something called structure factor, capital F, HKL. HKL is the indices of each peak. This is over the entire diffraction pattern, and this is the scattering from each atom. So when you're finding phase, let's say you found quartz, so Si and O, what is the atomic scattering coming from Si atom and the O atom? And here the Bragg angle at which those happen, the wavelength like copper you're using, and this expression is phase factor. So overall, this is calculated within your refill program in a fraction of minutes, seconds, I should say, the structure factor, when you load your phases. And the intensity comes from right from there. The absolute value of square of structure factor gives you the intensity. So that's how internally this program refill starts. So if I may present this with a picture. So when you load your phases, after finding the phases, the software has the idea. Like here are your peak position, just as lines, not as profiles. So that's step one that has happened inside the program. It knows where to build the peaks. Next, you need to give these straight lines some shape. And usually you use Gaussian and Lorentzian, a mix of these two mathematical functions. So remember, when you go inside the program, you're using something called pseudo-void function or a number of other functions, Pearson 7. These are very popular. The most popular functions, Pearson 7 and pseudo-void, which is a mix of the two mathematical functions, the bell shape and the sharp. And you can see in this picture, I'm trying to show pseudo-void function, which is a mix of Gaussian plus Lorentzian function. So now you had these lines coming from integrated intensities, the structure factor, and you have shapes. So you have now peaks, profiles. So, but they're still not connected. So you have some idea, the software has some idea from the phase. You have peaks at some distant Bragg angle where the X-ray diffraction conditions get satisfied in your pattern. So then you need to add those points. You need to add these peaks. So the software uses a background function, usually a number of background function. Again, you have a choice there. So next time when you go, you'll see what those choices mean. It could be beta spline, polynomial, inverse polynomial, or even FP methods for using your instrument parameter. But the idea is to generate any kind of background that that is coming from your instrument because of Compton scattering, amorphous phases, sample holder and capillary electrical noise of counting circuits. So in this way, you got the idea, like a number of refinable parameters are contributing to my building my model. So just in line with that, so on and so forth, what are your refinable parameters? You got the idea, the crystal structure parameter, lattice constant, atomic coordinates, profile parameters, which contribute to peak shape, background parameters, thermal parameters, occupancies, preferred orientations. So again, I repeat, the purpose of this slide is to show that you have all these controls in a refill refinement to fine-tune your model to fit on the diffraction pattern that you obtain from your instrument. So let us capture those brief but critical moments that typically go unseen when the phases are loaded and calculated pattern starts to converge with your raw data. So your raw data here, I'm showing in so that we can capture that moment in red dots, and blue is your model or the calculated data. So first you have a fixed unit cell coming from the phase you chose, but that unit cell increases in this case, and your peak shifts to the left because the D spacing is higher in the left direction. This is 2 theta. So you see, as soon as you load and you allow the unit cell to be refined, the blue went right on top of the red. We still are lacking the intensity. And as you remember, intensities come from square of structure factor. So structure factors, because you have chosen phases or your database with crystal structure, which is like inside the database as shown here, unit cell, XYZ position. This is lanthanum hexaboric. So all those information are inside the computer. Software immediately utilizes that and fills that gap from blue lines not covering the intensity to now beginning to cover for the intensity as shown in the second one. So that's what is going on within fractions of minutes, I can say now, because now it's more than seconds inside your program, and you finally get a good, well-fit model. But just to capture some windows in the program so that you see what I'm talking about, scale, which is you have 5, 6 phases. So you're refining those phases. You're refining their lattice. You're refining peak shapes, and they are inside the program. What peak shape? For example, pseudo-void or like I mentioned, fundamental parameter method, peak shift method, background. So you're using them. You are the one who are going to go and say, fix or refine. So these are default on in most of the program these days to make it easier for the user, but you can switch them off or on based on how you want to make the refinement go. Similarly, there is a texture button, and you can notice it says fix here. Now you could go, once you find the preferred orientation, to switch them on by right-clicking on it, for example, in a program. Right or left, it's just specific to a program. And if you don't have the crystal structure, this rate will automatically be doing something called Pauli or labile fit. And then you will fit your pattern. The blue one is here, the experimental or calculated data or the model, and red is your real data from, and there's the minimum. The differences are minimized. And one way to quickly look at what is my difference pattern. Are there still quite a bit of difference, like in this one? So you will go back and see, is there a preferred orientation here? Is it the right phase? A number of things you can go back and forth and fix it to get the model almost matching the real data. And then there are mathematical parameters such as RWP, RPS. RWP, for example, stands for residue on weighted profile. Remember the equation 1 I showed you with the picture of Dr. Reedwell? R is the residual. How close is my model to the actual data? And lower the better, like below 12 in boundary refraction. S is goodness of it. 1 is like perfect. We don't want to be perfect. It's not possible ideally. So somewhere in the range of less than 2, for example. Now, these numbers are more flexible based on the quality of data. So there is not a general saying you have to have a number before I will accept your publication. So we have seen this. Now let's see in like a movie, in any program, how would you do rate refinement? I'm sure whichever software you're using, you have used some of these functions and seen. So let's go into that. You will load a data in the software. For example, let's keep it simple, mixture of 2 phases. You will identify these phases in the software using a search match function. Mixture of 2, choose the database, and ran. The software is looking to identify these phases and comes up with anatase and rutile on the candidate phase list. We double check, yes. Always make sure checks, it's not auto. You have to ensure these are the phases. There is no such thing like always correct if there are multiple phases specifically. And we are checking they have crystal structures. Both of them have crystal structure. We move to WPPF. In this case, it will be Readwell because both of them have structure. And you can see scale, lattice, and profiles are being refined. We say simulate means show me the beginning of the model. And then we say refine, which means refine, in this case, scale, lattice, and profile. And we get the result. This one was usually very much in the default mode of the software. You didn't have to go through all the changing any variable. And such is the case when you have simple mixture of phases. But when you have a number of phases, you may utilize some more features, a number of features in the read pool. So let me show you a little more complex or people who are doing more than 5 phases. This is a clay or mineral sample, and you have a number of phases here. So you have to make sure you identify the phases which are common in the clay or mineralogy. You don't want to identify phases which are not heard of or which are not matching well. Well, that comes from your information of your material. And with some practice, you pretty much start doing the right phase analysis, and then you will go and perform a readable, you employing the right tools, such as when to refine which one, preferred orientation, and you would get the full results. So quite a task done by readable to tell you the phases that you are present. And like I said in the beginning, you can always create your own mixtures to ensure that you are using this software in the optimal way. So now we have seen 3 methods in quite a detail: RIR, readable, and calibration. And the question comes, what is the right method for me? So let's kind of delve into it, give it a little time to see. RIR. So when I saw the poll, so some people are using just 1 or 2 phases. I believe in those cases, you're not going to have much overlap of peaks. So easy to use, no crystal structure needed. And if you have simple mixture of 1 or 2, I mean, 1 is almost 100%, of course, 2 or 3 phases, and there's no overlap. But there's one more caveat: if there should not be any preferred orientation, then RIR is a good technique to do. In that case, if it is beyond 3 phases or 4 and severe overlaps, then the accuracy goes low. Preferred orientation can cause incorrect results. It becomes semi-quant, clearly. Not much useful when you have more than 4 phases. So I would say from my experience, something like that. Readable, quite a king among them if you have these situations. Relatively high accuracy. Reflection overlaps best handled. The effect of preferred orientation can be corrected. So readable is perhaps the only software which has function, March Dulles function, to correct for preferred orientation among the 3. You can't do preferred orientation correction with calibration or RIR. So it is best. It is best when crystal structure of all phases are known. So except the exceptional case that I mentioned, such as non-melanite, where there is no crystal structure known, the database usually have crystal structure, or you should emphasize to buy databases with crystal structure so that you can get the structure factor and hence the correct intensities. But it has a learning curve, the readable, I would say. For getting good results after readable, it takes few time and practice to get there. Calibration curve, perhaps the highest accuracy among the 3, if the conditions are met well. But so let's point out what would make you get a very good calibration curve. It requires a set of calibration sample, so you should have them, which is a big limitation. For example, if you are a mineralogist, you are doing mixture of 7 minerals. You generally don't have minerals in pure form to create a calibration curve of one of the minerals. Let's talk about kaolite. You don't have a pure kaolite, so you can't get kaolite numbers because you can't create a calibration curve for a kaolite or in any smectite or illite, for example, or in cement C4AF or C3S. Excuse me. Constructing calibration curve can be time consuming. You have to be very careful about the same metrics. Otherwise, there will be different metrics can contribute to the background, and the linearity of your curve may be lost or degenerated. Absorption and matrix effect can cause errors. So it is best for a small range if you could get, but often these conditions can be violated due to absorption effects, preferred orientation, multi-phase interaction, matrix effect. So choose carefully a peak, keep the matrix same, make sure that peak doesn't have preferred orientation in the unknown that you will bring in. So you create a calibration curve and you bring an unknown sample which has a preferred orientation on that peak, it's not going to work. Particle sizes are same. Peak issues can be handled. Don't select a peak which has slight overlaps. Broadening has happened due to crystallite size. Background errors due to matrix being different. For example, you created a calibration curve with certain matrix and you don't want to change it. Again, calibration curve also needs to be rebuild in 6 months or 12 months due to drift issues, noise, or misalignment of the instrument. So make sure you're taking care of the instrument issues in 6 months or a year. That's something you can decide based on the performance or the age of your instrument. Any questions at this point of time?
So Akhilesh, we are at 55 minutes in. So
okay,
we need you to just keep moving, and we will be recording all the questions. If we have a couple of minutes before when you wrap up, we'll go through a few questions.
Thank you, Tom. I can understand that. Let's kind of move to talk about something that you may not have heard a lot, direct derivative or DD method. Very simply, because I've used this FHKL before, it will be easy for our audience today to understand. The basic principle behind DD method, as developed by Dr. Hidayo Toraya, and referenced here. Remember, the structure factor and the square of it is proportional to the intensity. Well, he further took this idea and say it is also proportional to the sum of the square of electron density. Well, that gives a clue. If it is also proportional to electron density, that means that we can find the percentage weight of each phase just if we know their chemical formula. So that's the idea behind this technique. Very well established technique now. And so total number of electron is proportional to the total weight of electrons. As long as you know the chemical formula or rough chemical formula of the species that you're trying to quantify, you could use this method. So let me just mention very quickly how to use this method. For example, you have a mixture of phases. So you have two scenarios here. One, this is a mixture of two phases, and it could be extended, the idea to be over 5 phases. If you have these pure phases to yourself, let's say in a bottle, you have now phase A, phase B powder, phase A powder. So, and you roughly know the chemical formula. Let's say this is quartz and this is graphite, and you know the graphite is C and quartz is SiO2. Then any mixture of these two, when mixed together, just by knowing the chemical formula and refining the scale factor, we would know how much they are present. Now you will say, well, that's not the situation always possible, that I don't have the pure phases with the chemical formula known. You can also do one reverse thing. You can extract the profiles. That is, you read this profile, and by matching them, because you don't need crystal structure, you need like phase ID, for example, to match them, you can extract that pattern, which means take it out from your mixed pattern, your individual patterns, and then any mixture of these in further experiments, you can tell how much of these two are present. The only caveat is you know a rough chemical formula of those extracted phase out of your pattern. Hope that makes it clear. So I do want to do a justice by saying DD method in a nutshell. The DD method requires either single phase XRD pattern with defined chemical formula or the deconvolution or extraction of the individual phases, phase profiles from the complex multi-phase diffraction data. So when would you use this? What kind of situation will demand the DD method? Texture or large crystallite size sample, crystal structure database or RIR are not available, then you could use because you have your own patterns with a chemical formula. Amorphous or trace phases, perhaps single most situation where you can do, where WPPF is difficult to be applied. Shall we go into the question, Tom, quickly?
Yeah, so we're going to launch this really quick, and then so the question here is, have you ever heard of direct derivation? Have you ever used it? And so I kind of have an idea of what the answer is going to be. and it is, in fact, exactly what I suspected.
Hadn't heard of it, yeah. Well, good that we brought it to floor then, this method.
Yes. All right. So in an effort to continue moving, I'm going to end the poll. Yes, and virtually everybody in attendance has either not heard of it or does not use it at all.
Good.
So with that in mind, Akhilesh, we need to hustle through your next set of slides. We may have to skip the kind of the case studies you have at the end, just for our attendees. Okay.
Sure. Will do. Okay. So we promised amorphous phase quantification very quickly. There are two methods: crystallinity analysis, which is rather straightforward. For example, in this pattern, the 3 peaks which are crystalline, you find the integrated area of those crystalline peak and divide by the total area, which includes now the green amorphous area. So that's a pretty straightforward. The programs can do it for you. Amorphous phase, by the way, is like no lattice structure, just a blob, like a glass or wood. You could do them in Rietveld also with some method known as partial or no known crystalline structure. Essentially, you make a CIF file, like you make a crystal structure out of it in a large space group such as P1. P1 or P bar 1 centrosymmetric are fundamental space group representing lowest symmetry, so you can fit any amorphous into them and giving a unit cell. Then saving this as a CIF, then you essentially created sort of a structure with unit cell and space group, and which can be utilized to quantify the amorphous in your sample. I will show this quickly with two examples. Crystalline and amorphous peaks are shown here. Two amorphous humps, a crystalline phase, blue peaks, and what is the crystallinity? The software will calculate it as 67%. Moving on, limit of quantitation. This is DD method approach. You have a zero crystalline material here, and you have a 33% crystalline material here. So remember I said like you could extract these crystalline peaks of indomethacin out of this, and the amorphous is available. You have the idea. Pharmaceutical drug companies know, for example, what amorphous they are adding, so they have good idea of the chemical formula. And just by now, any ratio of the two can be easily calculated, for example, with the C2 function of the DD method. The expected values were in the tune of 3, 2, 1.5, 1, and 0.5, and the measured one came out very close to them. And still, we have to remember that still they are modeling technique, and these numbers are very good. That's one take-home message also. We do not want to expect always 0.5 equal to 0.5. You can get that, but more practically, it's within 1 to 3% error range. Common mistakes and solution, how to handle peak overlap, preferred orientation, and microstructure effect. Very quickly, I'll go this because this is one of the things we promised to show you. One of the things is peak overlap, and most of us know, for example, peak A, peak B, if they overlap, they would look like this purple overlap peaks. And one way to handle the peak overlap is Rietveld, because it considers the whole pattern, not all the peaks of the two phases will overlap. So it is one of the best techniques to use in the case of having severe peak overlap. If you're using RIR, you don't want to choose a peak with overlaps. And of course, you don't want to make a calibration curve with overlap peaks, because that would always give you wrong results. On the instrument part, you can use tighter slit, narrower slits. For example, in Miniflex, you could use one instead of 1.25, 0.625. But there is a limitation to that. But the good part is the whole powder diffraction pattern always will have unique peaks, not all overlap. So you got the idea when to use what from this. How to handle preferred orientation. So just very quickly, preferred orientation is when your peaks, when your crystallites lie in a certain direction, like this are showing flat OOL, OO3, OO4 direction, for example, then your peak is enhanced for that particular HKL instead of being the normal peak. Again, Rietveld can handle this very well. The two other methods you want to avoid on this peak, a calibration curve and RIR. You don't want to choose a peak which has a preferred orientation. Rietveld has a function to give the preferred orientation of that peak, and software can take. But I also want to mention at the sample preparation level, and it was covered in our first webinar, and feel free to ask us. You want to try preparing your sample with minimizing the preferred orientation, and there are several techniques to do that. Yeah. Microstructure effects are broadening of the peak due to either overgrinding or stress. Some of these things are inbuilt and hard to remove, but on your part, you should be aware if it is happening. One way is to reduce them is to use a instrument standard. So at least you can take out the contribution from the instrument. Usually silicon or lanthanum hexaborate are employed to remove the instrument contribution. So you know now what is instrument contributing, and you could take care of. But this is one of the hardest one to be avoided by us because we can't change the very nature of our crystallites, but it's good to be aware of that. So the three shown here together, and it is available to you. We mentioned that, what it would be, and it's good to keep them in mind. Tom, if you allow me, I will just pass through this case study in a minute. Would you?
Let's do it in like 2 minutes if you can, KSK, or Minikilesh, because we're
Yes,
already
yes.
over, and I don't want to inconvenience our attendees.
I'm also sorry about the inconvenience, but let's do it. So we talked a lot. I think people would love to see one example. How would they approach? It's an example using cluster analysis and template approach. In case of, for example, in mining or cement industry, for example, I got 16 samples from one customer, and they wanted to analyze this, and they said, "Oh, doing refill in all 16 of them is too much work for us. Is there a better way to approach this?" So collected good data, 16 minutes, and then the software can show you all the 16 samples laid down in this way, vertical offset. And you see a lot of them are same and some of them are slightly different. And using a program such as cluster analysis, you could divide, like, for example, 4 sets, 1, 9, 11, 12, 2, and 10 are of same type, and so on and so forth. There are 4 sets of 4 similar type. Now you could divide them into set A, B, C, D, and use a macro or a template in the read-fill refinement, which are available, to do it in like a batch. For example, 1, 2, 9, 10, 11, 12, these 4 numbers look same as I showed by cluster analysis. And yes, I find tantalum and tantalum oxide as the 2 phases that represent them. So you could use the read-fill analysis, just make a template and load all of them in one shot. You don't have to do each one of them, and it will tell you the total weight % of each one of them, the tantalum oxide and tantalum, and it can also represent it nicely in this sort of graph, each of the samples 1, 9, 10, so that you can quickly see in one view like that. So such template or macros can be utilized to do things where we have a data that can be divisible into a sets of, such say, 6 phases of same type or 8 phases of same type. Could be cement, could be minerals, or could be battery material, where you have such a choice to be made. Actually, that was it. Any questions?
Okay. So since we are at 2:06 here, I'm actually going to not take any questions. So, Akiyoshi, you've got about 30 in the list. So to everybody, I apologize that we weren't able to take questions, but I don't want to keep everybody significantly longer. So Akhilesh will be taking these and he'll distribute them amongst his colleagues in the applications lab, and everybody will get answers directly, but I do apologize. So with that said, again, thank you for joining us. A recording of this webinar will be available tomorrow, and an email will go out to all registrants with instructions on how to watch that recorded presentation. And finally, we'll be hosting the 3rd session of our Practical XRD with Confidence series, focusing on XRD for thin films. That's choosing the right measurement for structure, strain, and thickness. And we'll be holding that on Wednesday, June the 3rd at 2 p.m. Eastern, 11 a.m. Pacific. Thank you again for joining us, and we look forward to seeing you again in 2 weeks.
Thank you very much, everybody.